I am K. Sujatha, Assistant Professor and Head, Department of Mathematics, GTN Arts College, Dindikkal. Today we are going to discuss about LP space. Sigma algebra. What is sigma algebra? Omega is not equal to psi is a set. Sigma is a family of subsets of omega with first one pi comma omega belongs to sigma. Second one, A belongs to sigma implies A complement equal to omega such that A belongs to sigma. Third one, set of all the sequence n equal to 1 to infinity is a subset of sigma implies union n equal to 1 to infinity an belongs to sigma. Here sigma is called sigma algebra of subsets of omega. Next we are going to see measure space. What is measure space? Omega not equal to psi is a set. Sigma is a sigma algebra of subsets of omega. Here is a function mu from sigma to closed interval 0, infinity satisfies first one mu of pi equal to 0. Second one sequence n equal to 1 to infinity is a subset of sigma is disjoint implies mu of union over n equal to 1 to infinity an equal to summation n equal to 1 to infinity an. Here sigma additivity omega sigma mu is called a measure space. Next we are going to see measurable function. Here pair of omega sigma mu is a measure space. F is a function from omega to r is a measurable a set f greater than alpha equal to set of all w belongs to omega such that f of w greater than alpha belongs to sigma for every alpha belongs to R. The family of measurable functions is a real vector space. Next, measurable function statement 2. The family is closed under limit, that is a sequence of the function fn n equal to 1 to infinity is a sequence of measurable functions which converges pointwise to a finite valued function f, then f is measurable. Next, we are going to see one problem. The set of all omega, sigma, mu is a measurable space. If f comma sigma are measurable, then f plus g is also measurable. Here we have to take for all alpha belongs to R. The set f plus g is greater than alpha equal to union over beta belongs to Q set of all f greater than alpha minus beta intersection of g greater than beta. Next, we are going to see one problem. Omega, sigma, mu is a measure space. Let f1, f2, etc. be measurable and limit under n tends to infinity fn equal to f and f of x is finite for each x belongs to omega. Show that f is measurable. Hint, here we have to take for all set of all f greater than alpha equal to union over m greater than or equal to 1 union over k greater than or equal to 1 intersection over n greater than or equal to k set of all fn greater than alpha plus 1 by m. For any alpha belongs to R, we have to claim that set f is greater than alpha equal to union m greater than or equal to 1 union over k greater than or equal to 1, intersection over n greater than or equal to k, then function fn greater than alpha plus 1 by m. Proof. Here we have to take the subset for any w belongs to f greater than alpha. Now f of w greater than alpha. There exists m greater than or equal to 1 such that f of w greater than alpha plus 1 by m. Since limit n tends to infinity, fn of w equal to f of w. There exists k greater than or equal to 1 such that fn of w greater than alpha plus 1 by m for every n greater than or equal to k, which implies w belongs to intersection over n greater than or equal to k, the set fn greater than alpha plus 1 by m implies w belongs to union over m greater than or equal to 1, union over k greater than or equal to 1, intersection over n greater than or equal to k, the set fn is greater than alpha plus 1 by m. It is proved. Superset A W belongs to union over m greater than or equal to 1, union over k greater than or equal to 1, intersection over n greater than or equal to k, the set fn is greater than alpha plus 1 by m. Then W belongs to intersection over n greater than or equal to k, set fn is greater than alpha plus 1 by m for some m comma k greater than or equal to 1, which implies fn of w is greater than alpha plus 1 by m for all n greater than or equal to k. Now take n tends to infinity, we have f of w greater than or equal to alpha plus 1 by m, which implies f of w greater than alpha. Now, which implies w belongs to f greater than alpha. Since fn is measurable for all n greater than or equal to 1, the set of all fn greater than alpha plus 1 by m, which belongs to sigma for all m comma n belongs to n. Then set f greater than alpha equal to union over m greater than or equal to 1, union over k greater than or equal to 1, intersection over n greater than or equal to k, set fn is greater than alpha plus 1 by m, which belongs to sigma. Hence, f is measurable. Now, we are going to see indicator function. What is indicator function? The set of all pair omega, sigma, mu is a measure space for a belongs to sigma. Characteristic function psi a is the indicator function of a. Psi a is measurable. Now, indicator W denotes the smallest vector, subspace containing W in a vector space. Next, we are going to see simple function. Elements of set of all psi a is such that a belongs to sigma are called simple function. Next definition, a simple function can be expressed as f equal to summation I equal to 1 to k alpha I psi a, where alpha 1, alpha 2, etc. alpha k are different values and ai equal to set f equal to alpha I. Now we define integral over omega f d mu equal to summation I equal to 1 to k alpha I mu of ai. If the right hand side has a meaning. Now, next one, in particular, integral over omega f d mu is meaningful if f is simple and non-negative, although it is possible that integral over omega f d mu equal to plus infinity. Next, integration for f greater than or equal to 0 measurable. For f greater than or equal to 0 measurable, we have to define integral over omega f d mu equal to supremum of g is a simple such that 0 less than or equal to g less than or equal to f integral over omega g d mu. Next, we are going to see that f plus and f minus. F plus of w equal to set f of w if f of w greater than or equal to 0. Then 0 if f of w less than 0. Then f power minus of w equal to set minus of f of w if f of w less than or equal to 0. Then 0 if f of w greater than 0. We have to define f equal to f plus minus f minus. If f is measurable, then f plus and f minus are measurable. Next, integration for measurable function. For any measurable function f, define integral over omega f d mu equal to integral over omega f plus d mu minus integral over omega f minus d mu. If the right hand side is a meaning, then integration for measurable function, that is integral over omega f d mu is finite if and only if both integral over omega f plus d mu and integral over omega f minus d mu are finite. F is called integrable. Then integration for measurable function. Now, integral over omega mod f d mu equal to integral over omega f plus d mu plus integral over omega f minus d mu. F is integrable if and only if mod f is integrable. Then we are going to see that limit supremum an and limit infimum an. Omega is a set and a sequence. An is a sequence of subsets of omega. Define limit supremum an over n tends to infinity, which is equal to integration over 1 less than or equal to k less than infinity and union over n greater than or equal to k an. Then next one, limit infimum an n tends to infinity, which is equal to union over 1 less than or equal to k less than infinity, intersection over n greater than or equal to k an. Then we have to see limit an, that is if limit supremum an equal to limit infimum an where n tends to infinity. Then we say that the limit of the sequence set an exists and has the common set as the limit, which is denoted by limit an over n tends to infinity. Next we are going to see what about monotone increasing. An is a monotone increasing means A1 is the subset of A2 is the subset of etc. subset of An, subset of An plus 1, subset of etc. Then limit An equal to union over 1 less than or equal to n less than infinity An. Then we are going to see that monotone decreasing. Like that, here we have to take A1 is the superset of A2 is the superset of etc. superset of An, superset of An plus 1, superset of etc. Then limit over n tends to infinity, An equal to intersection over 1 less than or equal to n less than infinity An. Then we are going to see the lemma, that is spare omega sigma mu is a measure space. If an set a sequence an n equal to 1 to infinity is a subset of sigma be a monotone increasing, then we have to prove that mu of union over 1 less than or equal to n less than infinity an, which is equal to limit n tends to infinity mu of an. Now, the pair omega, sigma, mu is a measure space. If the set an, where n varies from 1 to infinity, is a proper subset of sigma, be a monotone decreasing, then mu of intersection over 1 less than or equal to n less than infinity, an equal to limit mu of an, where n tends to infinity. For let Bn equal to A1 difference An. Then set Bn is monotone increasing. By lemma, we have mu of A1 such that intersection over 1 less than or equal to n less than infinity An, which is equal to mu of union 1 less than or equal to k less than infinity bk, which is equal to limit n tends to infinity mu of bn equal to limit n tends to infinity mu of a1 such that an. Then mu of a1 minus mu of intersection over 1 less than or equal to n less than infinity an equal to mu of a1 minus limit mu of an where n tends to infinity, which implies mu of intersection over 1 less than or equal to n less than infinity an equal to limit n tends to infinity mu of an. Tambi,